All right. How's everyone doing? Okay, kinda. So I want to just do a little bit of confidence interval review, and then we'll tackle chapter 8. Okay. So confidence interval review. So far we've created confidence intervals for p hat. Okay, or actually it's confidence intervals for p, I should say, based on p hat. And the idea here is, we observe a sample and its proportion p hat. Okay, and based on the sample, what can we say about p? And so whatever our p hat is, we're going to, basically what we say is, we are, blank percent confident that p, the population proportion, is between blank and blank. Okay, so this is our lower bound and our upper bound. So that's the statement that we end up making. We say, we're blank percent confident that p, the population proportion of whatever we're talking about, is between blank and blank. Okay, and the way we find our lower bound is going to be p hat minus our margin of error. Okay, which is equal to p hat minus z star times the square root of p hat times 1 minus p hat over n. And then our upper bound is p hat plus the margin of error, which is p hat plus z star times the root of p hat times 1 minus p hat over n. Okay, and so we can combine this, into p hat plus or minus the margin of error, or just p hat plus or minus z star times Right, is this okay? Okay, and then so we have everything, and then the z stars have 4 values. We've got z stars equal to 1.96 for 95% confidence. We have z star equal to 1.645 for 90%. Z star equal to 1.28 for 80%, and z star equal to 2.58 for 99%. All right. Does this This is good? Okay, so let's say, you know, we conduct a survey. Okay. We survey, we'll say 200 randomly selected people. Okay, we'll say out of the 200, we'll say 106 say they will vote for candidate A. Okay? So 106 say they will vote for candidate A. Okay. So we'll say make a 95% confidence interval for the proportion of people in the population who will vote for candidate A. Okay, so what should our first step be? What's that? We should figure out our p-hat first. This p-hat is our sample proportion. What is our p-hat? 106 divided by 200. We get a sample proportion of 53%, I believe. Okay. Make that larger. 0.53. Okay, so p-hat is 0.53. Okay, so we're going to make a 95% confidence interval, so that's going to be p-hat plus or minus z star. Okay, so we have p-hat is 0.53. What is the z star we're going to use? 1.96. Why is it 1.96? Because it's a 95% confidence interval. Okay, and what's our n? 200. So here it's just a matter of plugging in our values. Okay, so we have 0.53 plus or minus 1.96 times the square root of 0.53 times 1 minus 0.53 divided by 200. 0.53 plus or minus 1.96, and then let's compute this out. So it's going to be the square root of 0.53 times 1 minus 0.53, close parentheses, divided by 200. I get 0.03529. Okay, I'm going to multiply that times 1.96. I get 0.069. So I have 0.53 plus or minus 0.069. Okay, so my lower bound will be 0.53 minus 0.069. I get 0.461. And then my upper bound will be 0.53 plus 0.069. 0.5999 or 599. Okay, and so we end up saying I am 95% confident that the proportion of people in the population who will vote for candidate A is between 0.461 and 0.599. Yes. Oh, we should have checked the normal conditions. You are correct. We should have checked for the normal conditions, but we did not. But they are met. We're going to say it's a randomly selected population, or a randomly selected sample, so that's met. And you know, assuming the population is like a state or a country or something, you're going to have more than 2,000 people. Say our population is big. And then, and if we check for, is our sample large enough? We have at least 10 people who said yes, they will vote for candidate A, and we had at least 10 people who said no, they will not vote for candidate A. So the large sample condition is also met. Okay, is this okay? So our resulting confidence interval goes from 0.461 to 0.599, and this is our interpretation, that I am 95% confident that the proportion of people in the population who will vote for candidate A is between 0.461 and 0.599. Any questions on this? All right, so I'm going to give you some follow-up questions. So I'm going to just copy this and say this, whoops, wrong tool. So let's say this is my confidence interval. All right, so I'm going to ask you some true-false statements, and you tell me whether these statements are true or not, okay? There is a 95% probability that P, the proportion of people in the population, or population proportion, of candidate A supporters or candidate A voters, proportion that P, I'm going to just say, is between 0.461 and 0.599. True or false? There's a 95% probability that P is between 0.461 and 0.599. So let's see, true or false? Okay. All right, what do you guys think? True, false? Okay. All right, those of you who said, all right, well, the answer is false. Those of you who said false, why is it false? Okay, the answer here is false, okay? And the reason why is because the population proportion P is a fixed value. P is a fixed value. It is a property of the population. We just don't know its value. Okay? We do not know its value, but there's no uncertainty associated with P. Okay. Maybe to illustrate this, what I'm talking about. Here, change. Here it is. Okay. All right. So I've got a coin. All right. I'm gonna flip it. Before I flip the coin, I'm gonna ask you, what's the probability that the coin will land heads? 0.5, right? Okay. Okay. I'm going to ask you, what is the probability that the coin has landed heads? Okay. All right, so I'm gonna look at this coin. Okay, I'm gonna ask you same question. What's the probability that the coin landed heads? Okay, so before I flipped the coin, it was okay to ask what's the probability that the coin will land heads, and the answer to that was 0.5. However, after the coin landed, that became a nonsense question. There's no probability of the coin having landed heads, okay? The coin either landed heads or it did not land heads, okay? It was actually, it no longer makes sense for me to ask what's the probability that the coin landed heads. It either landed heads or it didn't land heads. At that point, all you can say, even though you don't know how it landed, you can say, I am 50% confident that it landed heads, or I'm 50% confident that it did not land heads. But it no longer makes sense to say there's a 50% probability that it landed heads, because it either did or it did not. Right? Does that make sense? Okay, so the same thing is true here, okay? The population proportion P, it's some number. It's maybe 62%, maybe it's 50%, okay? It's either in between here or it's not, okay? We're 95% confident that P is in between 0.461 and 0.599, okay? But it doesn't make sense to talk about the probability that P is in there or not. P either is in there or it's not. There's no probability, there's no uncertainty associated with it. We're 95% confident that it is between these two values, but that's all we can say. Okay? We don't know the value, but we're 95% confident that it's in between here, and that's what we have. Is that all right? Okay. All right, true or false? Let's see. Our confidence interval provides evidence that P is not equal to 0.45. Okay, what do you guys think? Okay, and the answer here is true. What? Okay, so basically, we are 95% confident that P is between 0.461 and 0.599, okay? So we are pretty confident that it's not going to be 0.45, okay? So, we are 95% confident that P is between 0.461 and 0.599. Okay? So, we are confident that P is not 0.45. Okay? So we can say we have evidence against P being 0.45. Okay. Is it possible that P is equal to 0.45? Yes, it is possible that P is equal to 0.45. Okay? But we have pretty strong evidence that it's not. Okay? It is possible, but unlikely. Or I shouldn't say unlikely. It is possible P is equal to 0.45, but we believe that it is not. Okay, based on the evidence we have, we believe it's not. So far, okay? All right, let's try another one of these. Okay. Our confidence interval provides evidence that P is equal to 0.52. Okay, what do you guys think? True or false? Okay, and the answer here is also false. Okay. So 0.52 is inside our interval. Okay. 0.52 is inside the interval. Okay, so 0.52 is considered to be a plausible value of P. Okay. However, the interval will never provide evidence that it is equal to some value. Okay. Okay, the interval can provide evidence of values that it's not going to be. So it can give you a range of non-plausible values. And you can say I have evidence against these non-plausible values. But you can never say the interval provides evidence that P is equal to some value. Is that okay? All right, here's one more. Okay. If we take another sample, another random sample, so there's a 95% probability. So because we're talking about a future random sample, it's okay to talk about probability. Okay, is this one true or false? Okay, if we take another random sample, there's a 95% probability that that sample's p hat will be between 0.461 and 0.599. Okay, and this one is also false. Okay, so our confidence interval is a statement about P and not about future P hats. P hats or any other value. It's not about future samples or anything like that. Okay, so a lot of you guys got tripped up on the conceptual questions in the midterm and things like that. I would say, review these statements. These are conceptual statements about confidence intervals that you should be familiar with. Yes?
Did you say that our confidence interval provides evidence that P could be equal to 0.52?
Could be. yeah, I guess you could say that. We normally just say we're confident that P is between 0.461 and 0.599, and I guess that's what it would say. So, yes. So that would be fine. Yeah. Okay. Is that all right? Then I'm going to begin chapter 8. And this is about hypothesis testing. It's already week 5. Can you guys believe that? And next week is the last week of session A. The final exam is 1 week from Wednesday. It's like, it'll all be over in 10 days. It's kind of, I don't know if that's a good or bad feeling, but I guess 9 days really. Yeah, 10 days from now you'll be, you'll have no more Stats 10 responsibilities, so. I hope the class has been somewhat enjoyable as far as you know, I don't know what your expectations were, but I hope it hasn't been bad. All right, so let me just talk about the big picture of hypothesis testing first, and then we'll get into how to actually carry out a test. Okay? So with hypothesis testing, you start off with a premise. This is called a hypothesis. You start off with a hypothesis, okay? And actually, you begin with a pair of hypotheses. I think someone is locked outside. Okay, so you begin with a pair of hypotheses. I guess nobody wanted to let that person in. Made it. Okay. So you begin with a pair of hypotheses, a null hypothesis and an alternative hypothesis. And this is, the null hypothesis is kind of some premise that you start with, okay? A pair of hypotheses, these are called the null hypothesis. Don't get bogged down with the terminology, okay? Null hypothesis H0 and alternative hypothesis HA. Okay. And you say, well, for now, I'm going to assume that the null hypothesis is true. And if I assume the null hypothesis is true, then I expect the world to look this way, all right? So you say, I will assume, okay, or I guess say to yourself, I will assume that the null hypothesis is true. And if the null hypothesis is true, then I expect, the world to, look a particular way. Okay? And then we say, lo, the world does not look this way. Okay? I don't know if we say that, but so, we say, if the null hypothesis were true, then I'm going to expect the world to look this way. And if the world does not look that way, then we say, well, maybe my null hypothesis is wrong. My assumption about the world is wrong. Okay? However, if the world and what it actually, what the world actually looks like and what I'm assuming to be true is very similar, then we have no reason to doubt my beliefs. Okay? Then I expect the world to look a particular way. Okay? And then we look at evidence, okay? We observe some evidence. And there's two possibilities, okay? The evidence is very different, or the observation is very different from what we expect. Okay, the evidence is very different from our expectations, and then this implies my assumption was wrong. Okay. Or the other possibility is the evidence is only slightly different from our expectations. Okay? And so then in this case, we have no reason to doubt our beliefs, okay? Reason to doubt my assumptions, or doubt our assumptions. Okay? It doesn't prove that your assumptions are correct, but we have no reason to doubt them. Okay? Okay? And does this line of thinking make sense? Okay? So it could be like, you could say, I'm going to assume that, let's say you have a crush on someone, okay? I'm going to assume my crush has good feelings towards me, okay? And then you'd look at the evidence, right? And then you say, okay, well, if this were true, what would the world look like, okay? All right, so one thing you could look at is like, oh, does this person respond to my texts within a few minutes, okay? And then you look at the evidence, and you, let's say you text someone, and that person takes a few days to respond, okay? Well then, in that case, the evidence was very different from what you were expecting, okay? And that would provide reason to believe that your assumption about how this person feels is wrong, okay? On the other hand, okay, let's say you're expecting the person to respond within 5 minutes. The person responds within 2 minutes. Oh, you'd say, oh, well, that does not differ from my expectations very much. So I have no reason to currently doubt the assumptions I have about this person, okay? Now later on, maybe certain other things conflict or whatever, but that's just that's a silly example, okay? But you can say, if we want to test out a belief, we say, well, what would we expect under this set of beliefs, okay? And then we look at the evidence, and if it lines up quite closely, then we've got no reason to doubt it. It doesn't prove that this thing is true, but we have no reason to doubt our beliefs. On the other hand, if the evidence we have is significantly different from what we would have expected, then this presents a problem. Okay? Does that make sense? All right. So how do we decide what is very different, or we might use the term significantly or statistically significantly different, okay? Very different, what we mean significantly different versus not significantly different, right? Okay, so let's, well, so to decide that, we have to know how much variation there is. And that comes from our understanding of sampling distributions. Okay, so let's apply this concept to hypothesis testing for a proportion. Sorry, my hands just started, whatever, okay. So when we're talking about a proportion, we're going to do hypothesis testing for proportion. We can say something like, I believe that the population has a certain proportion. We can say, you know, I believe that in the population, no, we'll say, in the population of UCLA students, 40% live in an apartment. I have no idea. Okay. Does that sound reasonable? Too high, too low? Who knows, right? I have no idea. I'm making this up, okay? So this is going to be our belief, okay? So we're going to put this into, this is going to be our null hypothesis. Null hypothesis, 40% of UCLA students live in apartments. Okay, so we will say the null hypothesis, H0, is P equal to 0.4. Is that okay? All right. And then our alternative hypothesis will just be the number 40% is wrong, okay? So say a different percentage, something other than 40% live in apartments. So our alternative here will be P does not equal 0.4. Is that okay? Okay. So if the null hypothesis were true, okay, I can take if that were true, when I take a random sample of students, we would expect what? What would we expect? What can we expect about p hat, our sample proportion? What's that? That it would be somewhat close to 40%, right? So if my belief about the percentage of students living in apartments is correct, then when I take a random sample of students, we would expect our p hat, whatever it ends up being, we would expect our p hat to be somewhat close to 40%. Okay, we would expect p hat to end up close to 0.4, right? So now there's this question of what is close to 0.4 and what's significantly different from 0.4, okay? So let's say you ask, you sample, I don't know, 150 random students. And we'll say, we'll say 68 live in apartments. Okay, I'm making these numbers up, all right? Okay, so what is 68 divided by 150? 68 divided by 150 is 0.453. So p hat is equal 0.4533. All right. So here's the question. Is 0.4533 close enough to 0.4? Or is it pretty different from 0.4? Yes, no? Okay. Well, okay, so this is the question I posed to you, and the answer is we don't know at this point. We have to do a little bit more work, okay? And what we're gonna do is we're gonna compare the difference between 0.4 and 0.4533. We're gonna compare that to the standard error, which is talking about the standard deviation of the sampling distribution. And essentially we can get a z-score for this value 0.4533. We can see how far away is this from the mean of 0.4, right? Because if our null hypothesis were true, we would expect our p hats to be centered around 0.4. Because it's a random sample, some samples will end up having more than 40% in apartments, some samples will have less than 40% in apartments. I happen to get a sample with 45% living in apartments, and I want to know, is that different enough for me to question my beliefs, or is this or am I gonna say this is not that different from my beliefs? Okay. So my p hat is 68 over 150, 0.4533. Okay. Our null hypothesis said that p is equal to 0.4. Okay. So how different is this? Okay, well, let's figure out the standard error. Standard error is the standard deviation of the sampling distribution. Okay, so we're talking about the sampling distribution if we believe the null hypothesis were true. So in that case, we're going to use the p that appears in our null hypothesis. So the standard error is going to be, I'm going to write p sub 0 meaning use the p from the null hypothesis. Okay. So my standard error is going to be 0.4 times 0.6, 1 minus 0.4 is 0.6, divided by our sample size of 150. So what is that? 0.4 times 0.6 divided by 150. I'm getting a standard deviation of 0.04. So far, so good? Yeah? Okay. So basically our standard deviation of the sampling distribution, or my standard error, is 0.04. Okay? Our p hat is 0.4533. Okay? So let's get a z-score for the p hat we observed. Okay, so my z is equal to 0.4533. So here, let's just talk about what our z-score should be. It should be what we observed, this is the reality, versus what we expected, right? Under, it's kind of reality versus expectation, divided by, to decide if it's a big difference or small difference, we're going to divide by our standard error, okay? So we have 0.4533. It's different from what we expect of 0.4, and we're going to divide by our standard deviation of 0.04. Okay, so I have, what was that? 68 divided by 150 minus 0.4. And we're going to divide that by 0.04. So I get a Is that coming from inside this room, the chimes, or is that, do they do that every, no, not every, really? It's 11:50, why would they be doing clock tower? All right. Okay, we got this, 1.33, this is our z, okay? All right, so our z-score for this thing was, okay, so what we observed was that, 45% of the students lived in apartments, okay? The associated z-score for that is 1.33. All right, so is that, would we say that's significantly different from what we expected or not really? Okay, well, when do we say things are unusual? If the z ends up being more than 2 standard deviations away, right? So what we can do is, and when the z-score ends up being more than 2 standard deviations away, what does that mean? That means the probability of getting a z, what's the probability of getting a z more than 2 standard deviations away? 5%, right? There's a 95% chance that it's going to be within 2 standard deviations. There's really only a 5% chance that it's going to be more than 2 standard deviations away. So we're ending up at 1.33 standard deviations away. We're going to say, well, it's there's more than a 5% chance that we get this. We can actually calculate what is the probability that my z ends up being 1.33 or more away from the mean, okay? And this is going to be what we call a p-value, okay? We can actually ask. So I'm going to flip to the next slide. Whoops. So we're going to say on the previous slide we got z is equal to 1.33. And we can say, what is the probability that a random z is 1.33 or more away from the mean? Okay, and so what this picture looks like is that we actually have to look up both sides. We would have 0 in the middle, and we would put 1.33 over here, and we want to know what's the probability of being out here. And then we would also put a negative 1.33, and we want to know what's the probability of being out there. Okay. And the reason why we look at both sides, because the alternative hypothesis that we said was p is not equal to 0.4. So in this case, we would be interested if p is much bigger than 0.4 or much lower than 0.4. So we are interested if p is greater than 0.4 and if p is less than 0.4. Okay, so we're going to look at both sides. So what is the what's the area over here to the left of negative 1.33? What is it? 0.0918, okay? And then because it's symmetric, we also know that this one's also going to be 0.0918. So my total area, total probability that, you know, basically the absolute value of z is greater than 1.33 is 0.0918 plus 0.0918, 0.1836. Okay? So this says that if p were equal to 0.4, okay, you know, the probability that a sample has p hat, you know, equal to 0.4533 or something more extreme or something more different, I'll write. So the probability that a sample has this just from random chance is 0.1836, okay? Does that make sense? So if my belief is true that 40% of UCLA students live in an apartment, whenever I take a random sample, I could get a bunch of students, a lot of students living in apartments or very few students living in apartments, right? That's just the nature of random sampling. And so I happen to get 45.33% of students living in apartments when I took a random sample. And so I can calculate the probability associated with that. And this thing is called a p-value, all right? And it says, well, the probability that just random chance alone will produce this kind of difference, it happens around 18% of the time, okay? And so because it happens basically, you know, with quite a bit of probability, I mean, it doesn't happen all the time, but it happens 18% of the time, I'm going to say that it does not cause me to question my beliefs about the probability being equal to 40%. Okay? So this basically says that we can get a p-hat of 0.4533 with probability 0.1836. Okay? So because this probability, the probability of 0.1836, the probability is 0.1836, this value is not small. This value is not small, so we will not doubt our beliefs about p. Which was that p is equal to 0.4. Because what we observed was not, according to the math, turned out what we observed was not that different from what we expected. Okay? All right, why don't we take a short break here? It's noon, so we'll say 5 minutes, and then we'll continue on with this topic.